last session, so I appreciate everybody being here. My name is Levent Akil. I work for Intel Corporation. I'm based in Munich. My team actually develops performance analysis and trading tools within Intel. I am part of the software solutions group. And today I will try to present you about why we are here, why Intel is involved in the gaming, or any other related technologies. So the title of my presentation is Who Moved the Goalposts? And I'm going to talk about the rapidly changing the CPUs and the gaming industry and the gaming business, and what is really actually affecting how developers do their job. And I will try to focus on a few things from our perspective and try to give you some ideas what to expect in the future. So just a couple of actually fun facts about our current process technology. Currently we are at the 45 nanometer process technology for the CPUs. I know maybe this sounds so techy for you and you don't care, but just to give you some idea, if you look at it, you can fit around 2,000 45 nanometer transistors in the width of one hair. So you can get the idea of the process technology of the current processors. So what I will try to do is give you some motivation and why should you care about this speed of change. And I will talk briefly about the early and the future approaches to multi-threading games. And then I will talk about the tools to make the job easier, how the tools can help you, and of course, briefly talk about the features and research that we are doing. So let's look at the motivation. And so if you remember, like maybe not so long ago, like a couple of years back, if you go to early Pentium 4 and earlier time frames, you remember there was always this gigahertz race, right? And we were always trying to increase the gigahertz of the processor and try to give you the benefit of more performance increase by the gigahertz. But what happened is we hit kind of the power wall. And then it didn't become reasonable and feasible anymore to increase the frequency. So we decided, okay, how can we give more benefit or more power to the developer? So what we have done is simply, by reducing the voltage and the frequency, let's say by 15%, we can add more cores, the same processing power in the processors. So we started the multi-core and the many-core era kind of started. And the paradigm shift here we are talking about is you won't be able to get the, even if you don't do anything, you were able to get some performance increase when the gigahertz increase, right? The frequency increase. But now, in the multi-core era, what happens is the frequencies don't increase as much. So what happens is we are adding more cores, and you have to benefit or leverage the processor power by introducing parallelism into your software that you're developing for the PCs. So, you can ask, why should I care? And of course, there are many answers to that, and I will try to give you some of them. And to summarize, average game development takes 12 to 36 months, and core engine technology lasts even longer. Intel's TikTok model, maybe you never heard about our TikTok model, but it's basically what we are trying to do is we are trying to introduce new microarchitectures, processor microarchitectures every 2 years. And then every other year, we are introducing a new process technology. I mentioned earlier that we are now at the 45 nanometer. At the end of this year, we'll be moving to 32 nanometer. Maybe it doesn't mean much to you, but what is helping behind the scenes is basically enabling us to give more power and more cores or more features to the developers to leverage. And we call this TikTok because it's working like a clock. TikTok, every year we do a new microarchitecture and a new process technology. And we hope that it will continue like a clock, TikTok, but sometimes it might be TikTok. Hopefully not. Hopefully it's not gonna be in a unsynchronized fashion, but we try our best. And of course, the best performance comes from the parallelism and understanding CPU on the PC side. And design decisions made for one microarchitecture can significantly impact other microarchitecture or any game development, any algorithms you're designing for other architectures. So you have to be careful the speed of change happening not only on the CPU side, but also on the game technology and game industry. So basically, what I'm trying to summarize is with the great power comes great responsibility. The change is happening quick, and how can you basically take advantage of this change when you are developing games or any other software? What I will try to show you is actually, we have developed this game engine, or what I should say, a demo, and it's available on our website. What we try to do is, we try to take that demo from single core or single threaded approach to multi-threaded. We try to parallelize it, and we looked into different ways. How is the best way? What is the best way to introduce parallelism to this particular engine or to demo? When you look at through the traditional structure, you do render, and then you basically update the matrices for the animation, right? And so in the most simplest case, you do render, and then you update physics, AI, and particles. So you can always download. We call this Destroy the Castle demo. I don't know how many of you heard about it, but anybody have seen this? Or anybody tried? Any hands? No, okay. So I would actually encourage you to go and download this and look at it and play with it. It is available. The source code is there. You can always look at it and what we have done and what we have tried to accomplish. So here, what we try to do is, okay, let's see what can we benefit from introducing parallelism to this particular demo on a 4-core machine. So what we have done is, if you look at it, in the simplest case, you render, you update the animation matrices, your physics, AI, and particles. And here, we use internal tools, what we call Thread Profiler. And we try to analyze thread profiler by using thread profiler, these particular game engines. Here, basically, everything is happening in serially in a sequential mode. So we only have 25% of the system utilization, and the benchmark takes around 20 seconds, 21 seconds. So and here, the idea is right now, okay, we want to leverage the underlying CPU architecture. And I don't know whether you're familiar with the processor technology or the processors coming up recently, but we just introduced or announced, like say, Nehalem, the code name Nehalem, or the official name is Core i7. It is around 8 core. Right now, the server side, the server processor will have 8 core in it. With the hyper-threading, what we call hyper-threading, if you remember from the Pentium timeframe, it is simultaneous multi-threading approach. It will have 16 physical threads on one processor. And so if you have a system with this kind of processor, or if you're developing on this kind of system, how can you leverage? And because just simply having a serial application just means that you are leaving most of the performance on the table, right? So what we try to do is introduce parallelism. So I just want to basically here introduce you the decomposition methods or models 101. And here, if you look at it, basically how to introduce parallelism, there are 2 basic approaches. And one of them is functional decomposition, and the other is domain decomposition. Maybe you heard the terminology like the task parallelism or the data parallelism. Task parallelism is basically a functional decomposition. What you do, you find the independent functional areas and try to run them simultaneously. Data parallelism or domain decomposition is also a kind of, you can call it like single instruction, multiple data, SIMT approach. You have a data, and you distribute that data among different threads or different tasks, which can run individually, right? So what we have done is, okay, when you look at this, we say, okay, we have different functional domains, and so we can basically run them in parallel. What we try to do is, okay, we create thread pools.